Hi guys. Last class I discussed about drift velocity. To discuss drift velocity, we discussed about relaxation time. Relaxation time is nothing but we're representing that as tau. So relaxation time, according to definition, the time taken between two successive collisions. The time taken between two successive collisions is known as relaxation time. So this is something is important. Please keep it this word in mind, back of your head, because by the end of today's class, you will understand what is the importance of this relaxation time. So by using relaxation time, we use the first equation of motion. With the help of the first equation of motion, v equal to u plus at, we derive drift velocity. So drift velocity equal to minus E electric field E tau upon m. So this is the mathematical expression for drift velocity. The drift velocity is velocity gained by the electron in the presence of electric field in an conductor. When you apply electric field to a conductor, so this is what everything I am talking about in this chapter. So when we apply electric field to this conductor, before electrons are random motion, but because of this external electric field, now these electrons starts to move one particular direction, and in that course the electrons will drift, they will be pulled in one particular direction. So because of that they have certain velocity that we known as drift velocity. Drift velocity Vd equal to minus E, here the E is charge of electron and capital E is the electric field and tau is the relaxation time and m is the mass of electron. And negative sign tells about the direction of drift velocity is opposite to the direction of electric field. Yeah, velocity is a vector, so drift velocity is a vector. So drift velocity is very important. So after that, I tried to bring relation between drift velocity versus current. So this concept brought us drift velocity versus current. So in this concept, we came across different new formulas. So one by one I will write. Earlier we need to write that current I equal to Q by T. Before that, here it's very important to understand the dimensions of the conductor what I am taken. So here it is a conductor. So this conductor contains a length L and area of cross section capital A. A conductor of length L and area of cross section capital A. So that is a compulsory. Now to this conductor we applied an external electric field. So by applying the potential difference, here it is the battery. Now because of the external electric field, one side is some positive potential. So this side positive potential will be accumulated and here it is negative potential will be accumulated. So because of that electrons starts to move, electrons within the conductor. So they are drifting. So they are moving in particular direction. Now at here very important, the electric field and potential relation and length. Electric field, potential and length relation. So that we can write that electric field E equal to V upon L. So this is the very important relation we will use to derive this. So not only that, here we consider that as small n is the electron density. charge densities. Here small n is the electron densities or the charge densities. So here we have taken charge of electron, charge on electron, which equal to small e, and A is area and L is length. So here this characters small n electron density, number of electrons per unit volume. Suppose if you take that number of electrons as capital N per unit volume, you have to multiply that. So by using that relation, we derived about current. So what is the current expressions? Earlier we know that current I equal to Q upon T. So by using this relation, we got that current I equal to NEAVD. So this is the relation between current versus drift velocity. Current I equal to NEAVD. So after that, we derived Ohm's law. So Ohm's law, we know that V by I equal to R. But from this derivation, we got it that V by I equal to, so ml upon n e square tau A. So this is the new formula for resistance. The resistance, new formula in terms of dimensions, R equal to, so therefore R equal to, resistance R equal to ml upon n e square tau A. So here m is mass of electron and L is the length of the conductor, and n equal to electron density and E equal to charge, tau equal to relaxation time, and A is the area of cross section. So from this we rewrite this expression R equal to m upon n E square tau times L upon A. So this what we called as resistivity, because earlier we know that R equal to, resistance R equal to rho times L upon A. Now new formula for rho, so resistivity rho equal to m upon n E square tau. Now the resistivity purely depends upon which of the factors. Among this, m mass of electron is constant, and E's charge of electrons is also constant, and n, it is the electron density, number of electrons in the given conductor, that is also is constant. But the rho is inversely proportional to tau. So this is very important to which is I am going to discuss today is rho is inversely proportional to tau. Resistivity. So here I am asking a question. That question is, what is the cause of resistance? So what is the cause of resistance? What is the cause of resistance? So resistance is a property which almost all conductors, insulators, everything is having. So how resistance is occurring in a given substance? If you take copper, it's also having certain resistance, minute. And if you take nichrome, alloy, tungsten, which is having higher resistance. Now we are telling that those materials having resistance, right now we need to know what is the cause. So to know the resistance cause, yeah, this is the formula we need to go behind. So we need to know about this formula little deeper. So So if I rewrite that resistance formula, R equal to ml upon n e squared tau A. Resistance R equal to ml upon n e squared tau A. So this is for given conductor. So for a given conductor, so this value for a given conductor, this is remains same, it won't change at all. N is squared tau ml, the resistance value. But among that, if we can closely see one character, so that's the character is nothing but tau, its relaxation time. Suppose if I take the same diagram which I am using it here, so this is the diagram for a given conductor. So the length of the conductor is a constant and mass of electron is also a constant, and n for a given conductor, electron density, that is also remains constant, it do not change until unless if you change the length and area of cross section of the material, or you change the material itself, and area of cross section, and all these parameters which I am going to highlight with the m, n e square, l and a, though they all are constant, they do not change, so they do not change at all. But here the variable factor, is tau. So the tau is something is changing, resistance is inversely proportional to tau, or resistivity also. So this is the cause for resistance. So resistance is a property of a conductor by virtue of which is oppose the flow of current through it. Yeah, resistance opposes the flow of current. It comes due to collisions. So collisions are the basic cause of resistance. How these collisions happens? When a potential difference is applied across the conductor, the free electrons, they started to get accelerate towards positive potential, and on the way they frequently collide with the positive metal ions. That's the reason electrons, while they are moving, so they are colliding with the positive metal ions. So that collisions made their motion is opposed. So that is opposition to the flow of electron. Yeah, that opposition of the flow of electrons, which is only calling resistance. So resistance is nothing but the opposition to flow of electrons, or opposition to flow of current. So that occurring due to because of this relaxation time or tau. So this all causes due to only relaxation time. Now which are the factors this relaxation time depends? Factors which are relaxation time depends. So for a given conductor, for a given potential difference, everything is normal, it do not affect anything. But one important hidden factor, that is temperature. So temperature is a very important factor which affects that coefficient of resistivity, rho, which affects the resistivity. So here I am throwing a formula related to temperature and resistivity, which do not have any definition or derivation at here. The resistivity temperature relation. The resistivity rho at any temperature, sorry, at any temperature T. So I'm throwing a formula. So this formula, please remember if you are trying for the competitive examinations. Resistivity rho equal to rho naught of 1 plus alpha times T minus T naught. So here T naught is initial temperature and T is final temperature, and alpha we are calling as temperature coefficient. So here alpha we can call that as temperature coefficient, and rho naught is the initial resistivity, and rho is final resistivity after increasing temperature. So by using this formula, rho equal to rho naught of 1 plus alpha T minus T naught. So this formula gives the mathematical expression how the resistivity depends upon temperature. If the resistivity depends upon temperature, so I would encourage you to remember this instead of that. Since resistance R equal to rho times L upon A, therefore resistance at a temperature equal to resistance at initial temperature of 1 plus alpha times T. So this is something simple relation we need to remember. The resistance temperature relation. So here the character, if I say T is the temperature, the rise in temperature, increase in temperature, the rise in temperature, and alpha is the coefficient of resistivity, the temperature coefficient of resistivity, and R naught is the initial resistance, and RT is the final resistance after increasing temperature. So in this formula, if alpha is adding to R naught, if alpha is more and more and more, so automatically the resistance after increasing temperature is also increases. So the deciding factor at here, how the temperature is increases, so this is the factor known as alpha. Alpha, if you can say particularly the temperature coefficient of resistivity, it may be defined as the increase in resistivity per unit resistivity per degree rise in temperature. The increase in resistivity per degree rise in temperature. The increase in resistivity per unit resistivity I think I spelled wrong. Per unit resistivity per unit temperature. So if I can give the alpha formula also in terms of alpha equal to rho minus rho naught upon rho naught times 1 minus 1 rho naught times t minus t naught. So these are something different formulas. This is also I can write as 1 upon rho naught times d rho by dt. All are simply I am giving the formulas. There is no derivations, there is no particular rules and regulations, nothing was there. So these all are the certain relations. So but I would like to remember this formula, that is RT equal to R naught of 1 plus alpha T. So this is alpha means nothing but the temperature coefficient of resistivity. Now for metals, alpha value is positive. For metals, alpha value, the temperature coefficient of resistivity is positive. So that's the reason for metals, if you take metals as conductors, and when we increase the temperature, for conductors, for metals, the resistance of the metals also increases with temperature. Very, very, very important point. For metals, the alpha value is positive, the temperature coefficient of resistivity. So that's the reason when we increase the temperature, the metal's resistance value increases. It means the random collisions increases, the relaxation time tau value decreases. So at the end, the resistance value increases. So other than the metals, we are having some other materials. Suppose if I take for alloys, we are having alloys like magnesium and constant, and nichrome. So these are the different combination of the alloys which we are going to use for the practical purposes also. So for these metals, for these alloys, not the metals, for these alloys, this alpha value is very small. Means this alpha value do not change at all by increasing the temperature. So by increasing the temperature to this particularly, when the temperature increases, this alpha value is remains constant. So that's the reason these are the materials we used to prefer in the practical purpose other than the conductors. So to calculate the resistance and series combination, parallel combination, we need to do certain experiments in the lab. So those in the lab, we used to use certain apparatus. So those apparatus contains this magnesium, constantanum and nichrome, these kind of the wires, alloys only we used to prefer to use. What is the reason instead of using metals and alloys? Because these alloys are having the temperature coefficient value is very less. Means when the temperature changes, the resistance value do not change, unlike in metals. So finally I can make a comment at here. For metals, when temperature increases, the resistance value increases. But for alloys, when the temperature increases, so alpha value remains constant, it do not change. Alpha value remains constant, it do not change. And but when you can take one more for semiconductors, we will talk about semiconductors later. For semiconductors, So in the periodic table we are having natural semiconductors germanium and silicon. So these two are neither metals nor, so these are the semiconductors, neither metals, sorry, or the neither conductors nor the insulators, they come in between. So those known as semiconductors. To the semiconductors and insulators, particularly to the semiconductors and insulators, this alpha value is negative. The alpha value is negative. That is, for semiconductors and insulators, when temperature increases, the resistance value decreases. So this is something peculiar character for insulators and semiconductors. So that's the reason the semiconductors are very useful nowadays in all electronics, and insulators are the best conductors when they are, if you take to them at the negative temperatures. So finally I can make a comment that, so the alpha value is negative, so the temperature increases, so their resistance value decreases for the semiconductors and insulators. And but for the metals it's went opposite. When the temperature increases, the resistance value increases. There are the materials which temperature do not affect on the resistance, those are called alloys. So those alloys, magnesium, constantanum and nichrome, so these alloys are temperature coefficient constant, they do not change with the temperature. So here we need to look after certain graphs. So I am having three graphs. So the resistivity first, the resistivity versus temperature. So this is the graph, if we can go through. So this is the resistivity versus temperature. By seeing the shape of the graph, when the temperature increases, the resistivity value also increases for a given particular metal. When the temperature increases, the resistivity value increases. So this is the another graph. This is also for a metal, for nichrome, for an alloy. If you can observe the two differences in the graph. Let me put one more, the temperature difference for a typical semiconductor. Yeah, these three are the three different. One is, the first one is metal, the second one is an alloy, and third one is a semiconductor. So it's a metal, for a metal. So it's for an alloy. It's almost all constant. And it's for semiconductor. So in this case, the resistivity value rho is increasing proportionally when temperature is increases, and this is almost constant. The resistivity rho is almost all constant, the straight line, it's having very less slope. But here you can see the resistivity is decreasing. The rho value, the resistivity rho is, resistance also decreases. I would like to write rho, resistivity is decreasing when temperature is increasing. So this is for semiconductors, and for alloys this resistivity value is almost all constant. And for conductors, the resistance value increases when temperature increases. So this is all about the cause of resistance. The cause of resistance, finally I can conclude and say that this is Nothing but relaxation time or tau, the time taken between two successive collisions. So that is the reason for resistance and resistivity.